So today we're going to start our unit on organic chemistry. And I'm first going to start off by just saying a little bit about why do we have this entire branch of chemistry devoted to a single element on the periodic table. And it's because carbon is just an incredibly versatile atom, right? It's able to bond in many different ways that allow you to create essentially an infinite number of different types of molecules. And because of its versatility, it lends itself to being the type of material that would form the basis for biochemistry. So there's a lot of molecules such as fats, proteins, nucleic acids. All of these are organic molecules. Most of the atoms are carbon, hydrogen, oxygen, nitrogen, just bonded in different ways. So what I want to start off with in this unit is actually can be a fairly complicated topic, but it gets to the heart of why carbon is incredibly versatile. And to talk about this topic, we first want to go back and review a little bit about this topic of molecular orbitals. Okay, so hopefully you're familiar with atomic orbitals, all right? And atomic orbitals are just regions of space around the nucleus of an atom where an electron can reside, all right? And we learned that there's a couple types of orbitals. We learned that there's s orbitals. The s means sphere, and that would basically be like a ball around the nucleus, all right? There's also these orbitals called p orbitals, which are described as having a dumbbell shape. And one way to think about the shape right here would be just to take two balloons and hold them end to end, all right, with the part that you blow the air in the middle here, all right. So there's two other types, excuse me, of orbitals. Those would be the d orbitals and the f orbitals. We'll talk about those a little bit more. I believe you talked a little bit about those in the SL year, but first of all, whenever you have orbitals, they can combine to make molecular orbitals. Okay, so what I'm showing here are two individual hydrogen atoms. All right, so these two atoms would be kind of analogous to these symbols right here. All right, so here these two things are separate, and we know that they can those electrons can get shared to make a molecule. All right, so essentially what happens is that two individual atomic orbitals can overlap to make a molecular orbital. All right, and the electrons of the molecule reside in that molecular orbital just in the same way that the electrons in the individual atoms would reside in the atomic orbitals. All right, so what this shows is two s orbitals overlapping. All right, but we can have different types of overlaps. We could have an s orbital overlapping with a p orbital. All right, so let's pretend that we have an HF molecule. All right, and all I've shown is one of the p orbitals of the fluorine. All right, there's obviously a lot more orbitals of that fluorine atom. But when these things make a bond, there's a single electron in the hydrogen atom, and there's a single electron in one of the p orbitals. And what's going to end up happening is that you're going to end up having overlap between the s orbital of the hydrogen and the p orbital of that fluorine, and that's going to create this bond. And when these things overlap, you'll notice this side is a little bit longer now than this side. And that's because on this side, this is formed from that overlap of these two orbitals. All right. What about F2? All right. Well, when two fluorine atoms make a bond, this shows a p orbital of this fluorine atom and a p orbital of this fluorine atom. And if they align themselves like this side of one p orbital can overlap with this side of this p orbital, creating this area in between the two atoms, and that's going to be the molecular orbital of F2. All right, and what it means to be a molecular orbital is that's the region of space where the electrons that are being shared would spend their time. Okay, so there's two types of bonds that can get made whenever molecular orbitals are made. All right, the first type is what's called a sigma bond. All right, and when a sigma bond is made, essentially you can think of this as a head-to-head bond. All right, another way of saying that is when they bond in the direction so that the direction of the bond is along the axis of the orbitals. All right. So, for example, if I take just like this right here, if I show those two p orbitals and I draw the axis down the center of those p orbitals, you'll notice that the bond is along that axis. All right. So, in just an easier way of saying that is it's a head-to-head type of bonding. All right. So, so the thing about s orbitals is that they're symmetrical in every direction. So no matter how these guys were to bond, it would always be an s orbital. All right, and if this it would be a sigma bond. All right, so the last type would be an s orbital with a p orbital, and if they bond like this, that is, if you think about the axes of these orbitals, the axis of symmetry, well, there's infinite number of axes of symmetry for an s orbital, but one of them would be here, but the other one would go down the middle here, and this bond occurs along that axis. All right. So in contrast to that, there's what's called pi bonding. All right. So if I take two p orbitals, and instead of having them end to end like this, I held them so that they were parallel to each other. Notice that the axis of these bonds are now going like this, all right? And the overlap is not occurring along that axis, all right? If these things get close enough to each other, you can start to get a little bit of side-by-side overlap where the lobes of these things kind of start to merge together, all right? It's kind of hard to draw this. A lot of times you see it as like a smearing of electrons between these lobes right here. All right, so for right now, just realize that it's going to be a side-by-side overlap. And right now, I don't have any molecules that I can describe this with yet, because we need to talk a little bit more about the situations where you would see this. All right.